are going to do today we are going to go through some methodologies for efficient data cleaning and pre-processing techniques, especially for robust machine learning. But I want you to be aware that these methodologies can be used every time you are going to deal with noisy or unclean data, for example, for statistical analysis and things like that. But they are very, very useful and necessary in order to deal with machine learning models. Some reason why it's important. For example, there is a very famous quote. If you are going to use machine learning models, if you put garbage in, you are going to get garbage out. So this is what you're going to do. Even if you have a very excellent model, the quality of your input data can have a very strong influence on the reliability and also the model's predictions. So there is, in order to have very good models, it's not only to develop very complex or very sophisticated models, but the most necessary thing is to have clean data and high quality data. The reason to do that is because usually in your data, you may have bias or unfair data. So by cleaning and pre-processing the data, you ensure that you are going to have bias and fairness in your models. The other thing that can, the obvious thing is that you can have very high unclean and unprocessed data can have a very significant impact in your performance and accuracy of your models. So in this case, we are going to also show some examples where same exact data, how different a specific very simple model, regression model, can perform without clean data, and how significant it can be enhanced if you are going to use very, very simple strategies in order to guarantee this cleanness in the data. And the other one is because, especially if you are going to use with, if you are going to work with industry or any other critical applications, you have to have trust and usability in your models. So if you are going to use data, you have to ensure that you can be trusted and to be able to use them in other cases, except from make some simple predictions. So, and the other one is efficiency. So efficiency also makes it possible, if you have clean and usable data, to be able to use simpler methods, machine learning models in some cases, and simplify your model in order to increase the accuracy, but also increase the efficiency of the model. So today we are going to talk about two different categories of techniques, about cleaning and data pre-processing. See, we are going to separate these two processes. The first one that involves data cleaning is usually the process that involves identifying and correcting, in many cases, errors in your databases, such as in some cases you have missing or incorrect data. What strategy you can use to improve it or incorporate these inconsistencies. And then also for data cleaning, that it ensures data cleaning strategies to ensure clean, accurate, and consistent usable data. Even if you have clean data sets, sometimes in order to be able to use efficiently data model, machine learning models, you have to do some kinds of data pre-processing in your data in order to transform your data to be able to use them in the machine, to be able to be understood by the machine learning model. And I'm going to show some example in this case. So essentially, it prepares the input or the data for machine learning models. So we're going to start with data cleaning. What do we mean actually about data cleaning? How our data are unclean? For example, in some cases, we have missing values. It may be missing values. It's that part of your data is not complete. So you can enter this by different techniques like deletion or filling them with statistical values, or even use other predictive models in order to filling these missing values. The other thing that you need to be careful is outliers, how to handle outliers. And then we are going to go through some different techniques. We are going to define what the outlier is, first of all. And then we are going to go through some statistical techniques like Z-score, IQR, and other methods in order to be able to handle outliers. The other thing that usually exists in real world cases is duplicates. How to handle duplicate entries in your database, and then how to handle inconsistencies. We're going to go through in order to create a uniform set that can be used for machine learning. So this is the topics we are going to go through today in order to, when we are talking about data cleaning of your data set. Okay, first of all, starting with missing values. To be able to handle missing values is the first step and the most critical step in data cleaning, because the missing values can be leading to bias in correct results, and then or it can be, even if you have a lot of missing values, it can make your data set unusable for any statistical or machine learning model. So, and then we're going to go through, in the literature, there is primarily three primary strategies we are going to discuss. The first one is dropping the missing values, the imputation techniques, and then we are going to discuss about interpolation. About dropping missing values, this is the easy one and is the most straightforward. It's just don't use the columns or rows in your data set that have missing values. So this is the simplest one. It's very easy to implement, and it doesn't introduce any additional bias. Additional bias, it means in order to the way you process your data. But there is some significant drawbacks in case it can result in significant loss in valuable data. This is the obvious one. And there is not straightforward when the missing of data is not random. You have a pattern on how you miss data. For example, if you have a sensor that runs every day, 24 hours a day, and then you consistently missing values at night for some reason. So if you reduce that night, you essentially reduce half of your data set, and then you introduce bias in your data set because you are missing half of your day, which is cannot directly correlate with the other half, which is the day. Different scenarios run in the day, different scenarios run at night. So by having consistent, by having missing values that are not random, I mean random hour per day or things like that, which can be easily removed, it's a different deal. But if this missingness is not random, it can introduce bias in your data set. This you can use very easily. This if the missingness in your data set is very small in proportion to your data set. So, and then the other key reason is if the missingness in your data is not random. This is the most easy technique to use, but you have to be careful this case scenario. You have to be aware before you use these techniques that you are not, doesn't fill inside this, if it's not a significant portion, and if it's not, the missingness is not random. So you have to check. If the missingness is not random and the data you are missing has a significant part of your data, then we resort to a different scenario, like imputation techniques. Imputation techniques, we try to fill up these missing values with the existing information that we have in your data set. So for example, you can replace using either mean, median, or mode manipulation. So you can find similar, for example, in this case, if you have, for example, if you predict the weather, for example, and then you have readings from sensor every hour, and then you are missing an hour. So it's safe to see that you can take the mean between the 2 hours you have the data and be able to make some interpolation. You have to take the average between the 2 hours. Or, for example, you can take the average of that hour in the month, and you can take the median on mode value of that hour. So but this is how you can do it. Depends on your data. You have to make the decision. You have to. I will make you. The important thing about this lesson is I'm going to make you aware about different techniques, but in the end, you have to make the decision which is more appropriate for your data sets. Okay, so in this case, you are going to replace the missing values with either mean value, for example, if you run a sensor 24 hours, with the hour before and the hour after, or you can take the median value of the entire month for that hour, or you can take the mode of that hour. And then if it's too complex and then you cannot do that, you can use other statistical methods or even machine learning in order to be able to fill in these missing values. For example, you can see if your data follow like have a linear association between two values, you can very easily use a linear model or non-linear model to be able to make an accurate prediction or informed prediction about that value. So this is the second category on how you can use imputation techniques in order to fill up the missing data. This one, the positives is that it prevents data loss if you have significant loss in your data set. And this method can handle non-random missingness if done correctly. So you can use these techniques if the randomness is not non-random. But the thing is done correctly is the key, because you have to be careful, because if you are not done correctly, the negative thing is that it can introduce bias based on the assumption you make. For example, assumption you make, a simple one, you make, for example, you run a sensor 24 hours per day, and then you want to fill up a missing value for an hour. One day you can do it correctly if you take, for example, if that hour is in June, you can take the whole month of June and make the assumption, and you are going to be accurate. But if you make the wrong assumption that the whole year has the same, take the seasons out of the equation, you don't consider that you have seasons, and then, for example, 2 o'clock in July is different than 2 o'clock in December, and you take the mean for the whole year, you are going to introduce bias in your data. So you have to be careful what assumptions you make in order to fill up this missingness in your data. And then it's more complex to implement that just you have to make some informed decisions about your data. It's a little bit more complex to implement. You can use it if the missingness is non-random. And you have to be careful, you have enough data, you consider the data that you have enough data to make this assumption. Okay. And the last one is interpolation. For example, if you have a model that can predict, for example, in the hours of day, you have historical data, or you have a weather model that can predict what temperature is the hour with the rest of information. You can have linear interpolation. For example, you can choose like a straight line relationship between 2 points. And so you can if you have a linear relationship between your data, you can very safely assume that you have a linear relationship, and you can very easily interpolate the missing value. Or even the case if you see that you don't have linear relationship like a straight line, you have to do a little bit more work and to find the polynomial or spline relationship between them. You have a non-linear relationship between two values. So you have to use the statistical models in order to derive the interpolation between different values, and then you can use this model to handle the missing values on that. When you can do that, you can use it when you have a good then positives is that it can very easily provide good estimation on for time series data. So this analysis is very good for time series data. This for the correlation. And this methodology, because you can build statistical models, is not necessarily to only consider linear models, but you can also use non-linear models and be able to fill up values that follow non-linear relationships. Again, this is the negative one. It can work very well if the assumption between the samples is incorrect. So you have to be careful what assumptions you put in your data. So you have, but this is in order for you to have a very good understanding of your data. And then you have to, as I said, it's very, very well in the time series data, but it doesn't work very well in categorical data. So you have to be careful when applying this methodology in categorical data. You can use it for example, if you have sequential data like time series, and then use it when you have missing values, which are most likely to be a function of their nearest values. Usually this is the case for time series. Okay. So this is the three techniques that we are going to cover if you have missing values. So depending on the data, if you don't have any assumption of your data, just remove it. But if you have, if it's only a small factor of your data, if it's a larger factor of your data that is going to significantly impact your data set, then you have to use one of the two techniques that we discussed. Then you completed the missing values. The next step is to be able to identify in your data set to have outliers. Outliers is very important because they can be significant. It's a small factor of your data set that are statistically different from the rest of your data set. And these outliers, depending on your model, of course, can have significant effect in the performance of specifically your machine learning models, and also can lead into incorrect conclusion for your entire data. So very few values in the data as an outlier can have significant impact for the entire data. And then we are going to discuss some also three methods in order to be able to detect and handle the outliers. In this case, we are going to discuss Z-score methods, the IQR method, and also visualization that we are going to be able to use in order to handle the outliers in different scenarios. We are going to discuss what is the positive, negatives, and when you can use it. Okay. So for example, the first method is the Z-score method. Z-score methods is equal to, you can calculate the standard deviation of every data point in your data set from the mean. So for example, how many standard deviation a single point is away from the mean. Usually we consider an outlier if you have 2 or 3 sigma outside the mean. We're going to explain how you can do that. For example, this is the formula you are going to use for every data set that in order to be able to normalize and detect which values, which entries in your data set are considered outliers. So the values, it's like the Z-score for every data point. If you derive the value that you are interested, minus the mean value in your data set for a particular point, and then divide by the sigma, which is a standard deviation of your data. This is going to transform your data points into a new set of values with the mean equals 0, the mean value equals 0, and then you have standard deviation for each value, how far you are from this mean, this calculated mean. So for example, when you can use this, you have to be careful that in this assumption, as I say, this it will transform your data set into the mean value to be 0, and then each point will be how far away it's from the mean. So you will see the first assumption is that it's works very well if your data are normally distributed. Normally distributed, they follow this distribution. So if, the majority of your data set, you're going to see them in very close to the mean. And then as you go outside, you can see that you are going to go 1 sigma, 2 sigma, 3 sigma away from the mean. This is very simple to implement because you are going to follow very simple formula. And this is very so the majority of your data are going to be in very near to the mean, the 0, and then you are going to consider how many sigmas you are going to see. You are going to decide you are considered an outlier. As you can imagine, if you have very extreme values, for example, very extreme values, you mean the majority of your data is between 0 and 1, and you normalize, the mean is going to be very close to 0.5. But if you have a single value that is, for example, a million, if it's a million, and the majority of your values between 0 and 1, one single value you can move the mean value significantly. So this is very sensitive if you have very extreme values. And also you have to follow that your data actually follows the normal distribution. In our case, the majority of our data nowadays follow this kind of distribution. But you have to be very careful if you have these two cases. If you know that your data do not follow the normal distribution, and if you have very extreme values. Of course, use it when you have normally distributed data, and then you know that if you have normally distributed, you know the underlying distribution is also symmetric. Symmetric normal distribution. This is the case if you have used Z-score. So, for example, the other one you can use is to be able to have the IQR methods. The IQR method is to be able to this is a process, the way you can identify outliers. This is a process. So, for example, the first thing you have to do. So, for example, I will show this slide first. This is the normal plot of your data set if you use IQR. So, for example, in this case, you don't use mean values, you use median values. You have to sort your data set and find the median value in your data set, and then you can calculate the QR. The QR is the middle number from theory is the Q1 is the middle number between the smallest number and the median of your data set, and also represent the 25th percentile. The Q3 is also the middle value between the median value and the highest value. So it represents the 75%. So in this case, you find the median value, it's in this line. Then the half of your data, you calculate the Q1, which is the 25th percentile of your data set. And then Q3, it's the 75th percentile. In this plot, it's mostly the two Q1 and Q3 are equivalent, but you can have a more different distribution. So Q3 can be up to here and then the other way around. So in this case, for plotting simplicity, they are equal. And then you calculate the IQR. The IQR is between the difference between Q3 and Q1. So this one represents the 50% of your data. So you know that 50% of your data falls inside this IQR. So this box represents more than exactly 50% of your data. Okay. So then what you do? Then you also define the outlier bound. The outlier bounds is the Q3 times 1.5 and Q1 times 1.5. So you identify these lines is the value up to the 25th percentile times 1.5. And then there are Q3 times 1.5. So you plot this R, let's say. So this will present the rest of your 50%. Every value that falls outside this 1.5% plus times Q1 and Q3 can be considered an outlier. And usually it's plot individual. So in this case, you're going to find that you have 4 outliers in your entire data set. So this is the way you can identify the outliers. So I know it's a little bit tricky to understand. I'm going to show you an example. So for example, in your data set, you have this data. This is recordings from 1 to 46. The first thing that you need to do is to sort them from the smallest to larger number. Then you find the mean value. The mean value is, in this case, 13. The Q1, for example, from 13 to 1, it's 5. It's the 25 percentile. So 25% of around 13, it's around Q1 is 5. And then this around it's 20.75. Then you multiply. So between 20.75 and 5, you have 50% of your data set. And then you multiply this by 1.5. So you take 5 minus 1.5, this one. So the arm should be from minus 18 to 44. Every value that is outside this range is an outlier. In this case, you only consider to have one outlier. So 46 in your case is considered based on the IQR value an outlier. So you need, in this case, this is the way you can identify the outlier. So you can see they follow a normal distribution, and then up to a point, the values just simply double. Then you don't know, it doesn't follow the distribution of your data. So in this case, in contrast to the Z-score, this is very robust to extreme values. If you have extreme values, this is the way you can find based on your data. This technique is very robust to extreme values. It doesn't assume normal distribution in your data set. So if you know that your data set are not normally distributed, you can follow this method to identify the outliers. So in this case, it's also very, it's less effective in order to identify outliers in very small data sets. So you imagine if you have more data set, maybe 46 is not an outlier data. So if you have very small data set, this is not a very effective way to find it. And also assume that your data is unimodal. When to use it is when your data are not normally distributed, in contrast to the Z-score, and also when the robustness to extreme values is very important. So this is how we distinguish. How you make the decision is based on what kind of data you have. The last one is a little bit simpler. It was Wilsonization. And what you do, so for example, you just simply take percent, for example, in this case, you have the frequency of these values, 1 to 10, 11 to 20, and so on. And you see the frequency they appear in your data set. And you have this distribution. And then you can just make an informed decision that everything that falls under 1% appearance in your data set in simple values, you just remove it. The 1% is just, in your case, you have to make the decision. You just decide a threshold on the values they appear in your data set, and you just remove it from your data set. The positive things about using this value, it also reduces the impact of extreme values without completely removing them, because you're removing up to a threshold. And also, it doesn't require any assumption about how your data distributed. So if you don't know the distribution of your data, you have to make sure that you don't include any outlier in your data set. You can use this by this method. And also this, because you make the assumption on the percentage you're going to remove, if it's not done effectively, you can introduce bias in your data set because you're removing important information from your data set. And also you have to keep in mind that essentially you alter the original data because you are removing a part of your data which is important, which is in some cases is not desirable. You can use this method if you have to retain the overall structure of your data is very important. And also you have to reduce the impact of outliers without actually removing them is also desired. Okay, so this is the three methods that you are going to use based on your data set if you want to handle outlier. So if you know the distribution of your data set and you follow normal distribution, just use that score, it's the most effective. If you don't know the distribution of your data set and it's not following the normal distribution, you can select one of these two methods, the IQR or the Wilsonization. And then it's an effective way to remove outliers from your data. Okay. So we discovered you have a data set. You fill up the missing values. You handle the outliers by either removing them or I made an assumption here. You don't actually remove them. So I make a mistake here. You don't actually remove them. You replace the values to the nearest non-outlier. So I make this mistake here. So for example, you make a threshold. So everything that is above 120 or 111, you replace with a value 100, let's say. Okay, so you don't actually remove the values, just reducing the values of these data points to include them, but you actually reduce the value of it. We also included as a non-outlier value. So this is the difference. So the next step you have to check in your data set is to be able to see if you have duplicate data and how you can handle it in your data set. So what we are talking duplicates, it's you have to duplicate data with identical entries in your data set. So it's identical entries. And this is because you have overrepresentation of some feature in your data set. This can also introduce, it can mislead the analysis and also introduce bias in your data. Depending how much these duplicates are repeated. So obviously, if you have 1 million data points and you have one repetition, it will not have any impact of your data set. But if 10%, for example, of your data entries are duplicates, it will have a significant impact on the output. Okay, so usually this in our days, this can be done very easily using, for example, simple programming language like Python. With, for example, you can use Pandas and frame in order to be able to remove it very easily. The important thing is you have to make the decision if it's actual duplicate or not. If it's maybe multiple readings of the same value, actual readings that is repeated, or it's just, for example, an error in your code that is keep. For example, maybe you have a sensor in your data set, then a sensor that is recording, and for some reason it malfunction and keep recording the same value. It will keep recording, but the value is either incorrect or duplicate from exactly the same value. So you have duplicate. This will have significant impact on your data. So you have to identify them and then remove them. So how you can identify it is very easily nowadays using any simple programming language, and also can improve your accuracy, because you are not actually removing information, just removing duplicate information from your code. And also you have to be very careful, because duplicates in some cases can be are validated. They are not repetitions by an error or any other factor. They are actually reporting that they happen to have exactly the same value. So you have to have to be able to identify which scenario is in your case. In this case, there are, for example, certain data points which repeated without any variation. And also, they don't offer any, because they repeated exactly the same values with any other variation, will not have any, will not contribute to your models. And also, this is the duplication is not part of any natural aspect of your data collected. So you remove and then you have to, the other thing that you have to look at in your data, if you have a consistent data entry correction. So I will explain what we mean by that. And usually the consistency in your data set usually happens most commonly by human errors, or you have different data entry conversions, or you have a system glitch or an error in your data set. The most important inconsistency in your data, usually it's time. So for example, if you have time recordings from Europe, and then you try to integrate from US, for example, time is recorded differently. For example, in some cases, in Europe, you have day, month, year, but in some cases in US, you have month, day, and year. So there is a split between month and day. So this is not actually, it's not actually part of the human error, but actually in different data entry conversions. Or if you are dealing, for example, in data that records actual physical quantities, like mass, you may have kilograms, you may have pounds, and things like that. So you record the mass of an object, but you have a consistency in the way you measure. So you have to be aware what exactly is in your data set. And then you have physical, for example, system glitches that actually produce maybe invalid entries in your database. And then you have to be careful, because this inconsistency can significantly impact your data analysis. So for example, how you can deal with this kind of scenarios. The first case is, for example, you are especially dealing with data collected by humans, you have to be aware about case standardization. You have to compare all, for example, in some cases, you have to compare all characters to lower or uppercase in order to ensure uniformity. For example, when you are dealing with names or surnames, sometimes you may have, I will show you an example. The other important thing is about formatting dates. Dates are very important, because you have to ensure that all dates and times are following the same format across your database. The other one is, for example, you can have the same category represented by different categories. So you have to identify them and merge them, consolidate them into one representation. And also the other one that is very important, you see it very often, and it's not obvious directly, if you have spaces in your entry. Spaces can significantly impact your database, because maybe it can be classified as a different entry, a consistent entry, and so on. And the way you can use and solve all these problems is to be able to have a master directory. I'm going to show you an example. For example, in this case, you have this case standardization. So for example, every word in your database to be able to standardize to lowercase or uppercase, or in any other case form, but it needs to be uniform. For example, maybe or lowercase or uppercase, or only the first letter to be uppercase, or so you have to decide what is your case study, how every word in your database, or even if it's a category, it's going to be represented in your data. So you have to decide. The other one is to be able to decide how dates are formatted in your database. So you have to make a conversion. So for example, these two are exactly the same, but you can see different conversions. As to decide, for example, the first entry you see is always the date. The second one is always the month. And how you separate them is also important. By dash, by any other symbol, or maybe the month is always in spelled in December, October, and so on, or it's by number. So you have to standardize and the dates. And also, for example, you have to merge categories. In your data set, you may have different, for example, in this case, you have New York City, but sometimes someone may write it as NYC, some other entry may be New York City or New York. So you have to identify these scenarios that this category is then exactly the same by you, and to be able to merge all these categories. And the other one, when you see sometimes in your data, is to have the same entry followed by white space or a space. This is important because you are dealing with machine learning, and we are going to deal later on how you encode your data. For example, John with a space and John without a space is going to be represented in a different category or a different byte. So you have to be careful about strip white spaces from your database to have clean and efficient data. And this is a little bit tricky because it's not directly when you view your data, it's not directly located. And then, for example, you can have also a master directory because, for example, in some cases, some work you are dealing with data from different continents. So, for example, gray can represent and color can be written in different categories, and both are correct. So, for example, you need to be aware of the inconsistency in your data and fix them, and fix them by creating a master directory that every time you see a variation, for example, of gray or color, so that this is the convention that you are going to follow. So this is also important if you are dealing with real world data. So, for example, what is the why you want to use these techniques? It's because it enhances data uniformity and also improves the data accuracy of your analysis. I know that this can be very time-consuming, but you have to do it only once. And also, the other thing is that it requires deep understanding of your data. So, for example, at the end, if you do this, you have to be able to understand the data better than anyone else. Okay, if you don't understand the data, then you will not be able to rely and be able to make this conversion. So, important thing, you have to understand your data. And then you have to use it when there is actual irregularities in your data representation. And also, this is very important if the data set comes from different sources and conversion. So you have to follow these steps. If you collect data from even from multiple individuals, you have to follow this conversion because even in individual level, you can see this inconsistency. So now you follow all these steps, you have clean, complete, and hopefully unbiased data. So, and you want to use them in statistical models or machine learning. How you can do it? What are the steps if you have a clean data set to be able to convert it in order for a machine to understand? So this is the steps you are going to follow in order to convert your data set in a machine understandable way. So the first thing is to be able to transform your data set in order to apply different techniques in order to be able to meet some machine learning assumptions. The first thing is to be able to transform your data. Then you have to normalize and scale your data set in order to be more consistent and also balance the different numerical data. It's very important because, for example, in the first part, you may have categorical data. For example, New York City, the letter gray, or this as a letter cannot be understood by the machine. You have to convert it into numerical. I'm going to show you different machine, but then they have to scale it so every feature can follow the same scale. And this is very important because, for example, imagine all feature in data sets follow a simple conversion, numerical values between 0 and 1, -1 to 1, or 0 to 10. And then you have one class that can have measurements from 0 to a million. That single feature can have significant impact on your data. That's why you have to normalize and scale your data. And then you have different other categorical data, which are categories. How you represent categories in your data. And then when you convert it, how you make sure that all features in your data set are important for your model. How you say, do you use all features in your data set? Do you select feature? How you make the selection? And then we're going to discuss about feature engineer. Can you interpolate other features that are important in your data set from the existing data? And if yes, how you can do it? So, for example, the first step is data transformation. Data transformation involves in changing the scale or even the distribution of your data in order to better suit the assumption that centered machine learning models make. And the way you can do it is using three transformations. Can be log transformation, Box-Cox transformation, and Johnson transformation. How and when you can use it. So, for example, the first step is to be able to identify if your data is transformation. Okay. The first step. If yes, for example, see the representation. This is a representation of for mammals, the correlation between size and metabolic rate. If you report them and plot them, this is what you see from the size. So you can see. So even humans cannot make this assumption. So it's very easily to make a significant prediction or observation from this data. But with a simple transformation, you can see that this value starts from 0 is significantly increased. So, for example, using log transformation on the metabolic rate, you can have this. So, for example, you can, from pure reporting, if you log transform your data, you can have this very nice representation. So you can see the size and the metabolic rate of mammal follow a linear distribution, but in the logarithmic rate. So it's very obvious that they follow a simple line, but in the logarithmic scale. So it's very easily also to make predictions using this plot. And you don't actually, if you have a new animal that is not reported, you can very easily predict the metabolic rate or the size of the animal by only using this plot. But imagine doing that using this one, where you have more complex data. So transformation, to be able to understand the data and see what is important in order to transform your data is very important. The next one, what is the benefit of using log transformation? It also helps manage secure data that they have associations that are not directly obvious. It also compresses the scale of the data in order to make it very easily handled. The negative of this, it cannot be applied to 0 or negative value if you're using it. And also or you won't have enough meaningful results. And also, this may not normalize distribution if your data are very heavily skewed. Also, use it if your data is right skewed, tell to the right, or if your all data points are positive, and use this log transformation. What happens if your data are not logged, follow not right skewed, or they don't, or not all positive values are, they don't follow this distribution? you can also transform them using this box node transformation. This is a very flexible model in order to transform your data from any distribution to follow normality, follow normality. So if you have a data set that doesn't necessarily follow normal distribution, you can transform it using box node transformation to follow this normal distribution in your data set. Okay, this is the way you can use it to follow. But you have two negative things about this. It's also what is done is you have one parameter for L parameter where you can use in order to adjust it to be able to transform your data to normal distributed. So this is also dynamically determining the power transformation and also works also very well to non-zero data. Again, this method can handle the zero and negative values, and also the complexity in order to identify the correct L parameter in order to transform your data. So this is the negative. Okay, so you can normalize this data using these dynamic methods, but if all your data are positive, what happens if you have negative numbers or not all your data follow you have negative or zero value? Then you can use this Johnson transformation that is exactly the same thing, but also can handle negative, zero, and positive numbers. But for the positive values, not as well as the box node. So if you have zero and negative values, use Johnson transformation. If you only have positive values, use the previous. This works very well for a variety of distributions to convert into normality. And also the complexity also has the same negatives. The way you can determine the right parameters to convert the distribution. And then this is also maybe is too much if you have some very other simple transformation are sufficient. You also use this if you want to convert your data to normal distribution if your data contains negative values, and also if you need more flexible method to normalize the data. Okay, so you convert it from any distribution to normal distribution. You transform it into a more meaningful scale using logarithmic scale. And then, but this is not the only way you can scale your data. For example, you can follow other methods in order to scale your data and normalize it in order to be able to use in machine learning model. The way you can do this, usually we are going to discuss these three simple methods, which is min-max scaling, standard scaling, and robust scaling. The simplest one is the min-max scaling. Min-max scaling is, for example, the transformation is if you, for any data point, you subtract the minimum value and then divide by the difference between the maximum and the minimum. So everything that in your data will be normalized usually between 0 and 1, or you can, this is the way if you have negative number. Have positive number, you can just divide by the maximum value, and you have something between 0 and 1. It would be between 0 and 1 without including 0. But this is a more inclusive method if you want to guarantee that it's going to be between 0 and 1, especially if you have negative. It's very simple and intuitive. It's also preserved the original distribution. It doesn't affect the distribution of your dataset, which is very important. And also, this is the other thing that you have to be careful. If you have, it is very sensitive to outlier. So if you want to use this method, you have to deal with outliers before using this method. Okay, because it's very sensitive. And also, if you have outlier in your data, it's not very well if you have very large, if you have values that they follow very large standard deviation. The method I showed you before, that you have values, actual values that are beyond 2 or 3 sigma from your standard deviation. And this is very important if you want to preserve zero values in your data set. And also, the data doesn't contain extreme outliers. If your data contains extreme outliers, then you can follow other methods, like the Z-score normalization, which is exactly the same formula I showed before in order to identify outliers. Because if you identify outliers, you can also keep the distribution, but you have to be careful that the majority of your values will be very, very close to mean, which is the mean value of your data. So this again is the same formula as I showed before. You have a single value, subtract the mean of your data set, divide by standard deviation, and then you have Z-score normalization. This is the positive things about this method is the center of the distribution is around zero, guaranteed to be around zero. It also handles the outliers much better than the mixed-match scaling, because a very extreme outlier usually has a value of 3, 4, or even 5 from 0. So the values are scaled much more easier if you have extreme outliers. This doesn't normalize the negative things about this. The score is this, it doesn't normalize the distribution to a specific range, because as I said, it's open. You can everything around 0, but it don't guarantee that you don't know what is the range of your. It can be 1, it can be 2, it can be 3 or 5. You actually don't have close bound range for your data. And this also can be influenced by outliers if their outliers are very, very extreme. Okay, this use also again, same as before, when you identify outliers, you assume normal Gaussian or normal distribution in your data set, and then the algorithm will assume that the data is centered around 0, especially if you are going to use principal component analysis. Okay, so for example, the other thing is the robust scaling. Robust scaling is the methods that we used before using IQR in order to identify outliers. If you have identified the Q1 and Q3 your database, you can use that value in order to scale your data by any point in your data set, subtract Q1 and divide by the difference of Q3 and Q1. So this is the Q1 within the 25th percentile of your feature, and the Q3 the 75th percentile of your feature. When the positive things about this method is also it significantly reduce the effect of outliers if they exist in your data set and you want to keep them. So this method can handle very well scale and can handle very well the outliers in your data set. For example, it is very useful if you have a heavy tail distribution. So, for example, when you plot it, your data set leans into one part of you don't have equal representation of your distribution. Maybe you have collected more data. For example, if you have more collected data in the day rather than night, if you are dealing with temperature, it's going to be more sample due to the day, and then you gain more sample with higher value. So usually in day you have higher temperature. So you have to be careful with this one. But this method, normalization, can handle very well these heavy tail distributions. And also you have to be aware that this method doesn't scale the data against a very specific data. You don't have a closed range in your data set. And then also it cannot perform very well if your data do not follow non-Gaussian distribution. And also use this if your data contains many outliers, because it can handle them very well. And also can also reduce the impact of outlier in your analysis. Okay, so the other thing that you have to be aware, if you have categorical data in your data categories, you have data representing categories, and then you want to convert them, since machine learning models until now they can handle only numerical values. You need to figure out a way how you convert this categorical data into numerical data. How you can do it? You can do it usually with 3 methods: label encoding, one-hot encoding, and also targeting. What do we mean by that? Label encoding is, for example, you decide that, for example, your data has different color. You decide like red is always going to be equal 1, green is equal to 2, and blue is equal to 3. So you make the important decision that you are going to assign these specific numerical values in your category, in your class. It's also very simple to implement. It doesn't affect the dimensionality of your data. Usually it doesn't increase it because sometimes you will see other methods that significantly increase the dimensionality of your data. The negative things is that it implies an order relationship between, for example, if you see red is equal 1, green is equal 2, and blue is equal 3. So you see, if you, in some cases, you assume that blue is closer to green than it is red. Make it assumption. But in some cases, it may not be the case. The order in this case doesn't matter. But in some cases, some methods may make the assumption that, for example, blue is close to green or green is in the middle. In theory, a person can make this assumption or the algorithm can make it. But in some cases, it may be correct. You have to be a little bit careful about that. And also can lead to very poor performance if the categorical variable is nominal. For example, if you have nominal, in this case, it does actually matter the order, so you can have you can use this encoding. So what happens if the order actually matters, and then if it's what happens if you need a different method that can handle this kind of problems? And then you have one for encoding. I mean, for encoding that you can have transform this data into this vector that you have all zeros. For example, if you observe color red, for example, you can see, and you know you have only 3 colors. You can have these 3 vector of 3, 1. That, for example, color red is only represented 1, 0, 0. Green is going to be represented always 0, 1, 0. Like that. So you can only one, but you can create a vector that you know that the category is always going to be 1, 0, except the category is below. Okay, so this is one for encoding. So the positive is 1, it creates binary vector between 0 and 1, and then it eliminates any implied order. It eliminates the problem that you have red, green, blue in always this order 1, 2, 3. This takes away this implied order, and it is very suitable for nominal categories, which they don't necessarily have any inherent order. But the problem is that, imagine this case, we have 3 categories, and then you can have if you have 3 categories, then you have one for the vector of 3 values. What happens if you have 1,000, 100,000, or a million? And see how it can significantly increase the dimensionality of your data. So you have to be aware how many classes you have, because this method can significantly increase the dimensionality of your data. The other one is this is not suitable if you have categories that have many unique values. They have high cardinality. Also for the categorical values, use when the categorical values is nominal and the order doesn't matter. And the categories is the unique categories is rather small. Significantly increase the dimensionality of data. What happens if you want to use something similar, but without significantly increase the dimensionality of data? Then you can use this target encoding. Target encoding also means as a mean encoding. This is a way you can represent a group of categories. Categories. This is, for example, if you have high cardinality feature, and then when one code is not suitable. So, for example, if you have cities, you have many cities, and you want to encode for example, the average house. You don't take every city and you represent it with a single value, For example, New York City, this value, Boston, the other one, Nicosia, this value. You take, or either neighborhoods, you take the average of these, the house prices, because the values cannot be 0 and 1, and then you present the entire system, the average price that you find. For example, this is target. So you encode it based on different groups of features that exist in your set. So, and then you target it, and you can see significant difference. For example, the target encoding for New York City would be significantly different from the encoding of Nicosia. That's the difference in price or any other feature that you that they are interested in the RTW. But you can see the positive things about this method is, for example, you can capture information within the category, within the entire category, no individual interpretation, and then it can significantly improve the performance. It preserves the high dimensionality of your data set, but if you do not do it very correctly, if you don't do it correctly, also there is a risk of overfitting due to information leakage. Information leakage, for example, if you define by New York City, you have defined what are the boundaries of New York City, for example, that you are going to include in your target. Why only New York City and why not go a little locally by, for example, how close you are to the center, define zone like you have in London. So you have to be a little bit careful how you represent your target, your group of things that is going to be average in one category. So you don't need to be very specific, very small, or you cannot be very broad. You have to be a little bit careful. And also this requires very careful validation strategy, not to decide what groups of features are going to be encoded together. Use it when the categorical feature they have high cardinality. So, for example, in prices for New York City, it can have significantly different depending on the neighborhood, depending on, for example, which floor you are, and things like that. But for a prediction, you don't require this high cardinality. And then there is a correction between the category and the target value. So there is actually a correlation between the category we are trying to encode. Okay, so until now we covered how you can clean the data, how you can filter the data, how you can encode the data in order to be able to use the machine learning model. And then we're going to decide if every feature in your data is important for what you are trying to do. So feature selection is the next step of the process in order to reduce the number of input of variables in order to use it in the predictive model. It's also very important to remove any irrelevant or noisy feature or partially relevant, or even if they have a negative impact on your user. And then how you are going to do it, you are going to cover 3 methods, which is for filter methods, wrapper methods, and embedded methods. What is these methods? These methods is, for example, the filter methods is you are going to filter things using statistical methods, statistical model in order to assign a score in each feature. How you can do it, for example, you can do Pearson correlation, chi-square test, mutual information, or even ANOVA score in order to measure statistical significance between the input of your value and the output you are trying to predict. So, and then you say the score that you are going to select the top 10 feature based on this score, or the top 20 feature, the top 100 feature. Or you are going to remove that ones that they have, for example, their correlation have very small value. They have very small correlation between your input and output. This is the first way where you can make a selection, for example, depending on your model. Maybe you have enough resources to select only the most important feature in your data set. They want to make a prediction. Or you want to reduce it to a single, or you have to see the ones that they have a negative input. So this is how you are, this is a tool that will give you an association between the input and output. How many features you are going to use depending on the input and the output analysis. So this is also very simple to implement. It's also very fast and computationally efficient, which is very important. And also, but the negative one, maybe this is directly only consider the association between the input and output. But it doesn't take into consideration the interaction between. So you have to be careful. And also, it's only based on intrinsic properties of the data. You have to use it when you have a large number of features and you want to sort out and select the most appropriate feature. And also, it's very efficient way, very quickly filter out irrelevant. Okay, so if you want to make a more sophisticated method to select feature, then there is a wrap-up method where you, when you're going to follow these three methods, which is in order to be a selection based on the model accuracy that you want to use. There are two methods. Is the forward selection. The forward selection is, for example, you create your model with your entire set of features, and then you take out one feature and see how much impact your performance. If it has a high impact on your model, you keep. If it has zero impact on your model, then you can remove it. And then you keep going, removing feature until you are left with a set that you can no longer remove any other actional feature without having any impact on your prediction. So this is the forward. The other one is to go the other way around. Instead of removing features, starting from small data set, is to add features. Start from a very small data set, and then add features to see how they can improve your method or not. So you can remove add, and then you have the recursive feature elimination. That you don't add a single feature, you add a group of features. For example, you add a group of features, for example, if you are predicting house prices, maybe you add all features are related to how big the house. And all of them, and then see, you add or eliminate group of features that they represent more or less the same feature. So this is the fastest way you can eliminate. So the negative is this is more guaranteed to search for the best set of features, best set of subset for your prediction, and this also considers the interaction between the features. But you understand this method, especially if you have a complex model, this can be consistent, very expensive. Okay, and then it's also prone to overfit. We're going to explain what overfitting is. For example, if you have a data set. Overfitting is that your model gets very, very poor, but only if the data set currently have. It can achieve accuracy usually 100%, but performs very, very poorly with any additional new data. Okay, so this is what we mean overfitting. You can use this if you have a moderate, small or moderate number of features, and the computational resources and time that you have in order to build the model permits. If you don't have this kind of, you can use the other simpler methods in order to identify which features are important for your model. Then you have the embedded methods, where it's this is more or less automatic way for actual group techniques, which performs the feature selection as part of the model construction and things like that. For example, machine learning model, especially neural networks, do this automatically because you can assign, for example, you can apply last regression, which is stands for least absolute string-edge selection operation, which especially this technique adds the penalty equivalent to the actual value of the marking of the coefficient, and then you can adjust this feature, which are important, automatically as you train the model. And then when you actually train the model automatically, you can open the model and see how many features took this value, the marking of coefficient, to zero. Zero is automatically the last of the method, automatically discarded. So you can automatically remove them to the model and then retain them or use them, don't use them entirely. Then there is the ridge regression method, which also adds penalty equivalent to the square of magnitude of the coefficient. And then the coefficient also assigns the same factor, but so essentially none of them are eliminated, but the effectiveness of it are significantly reduced. Then you have other methods like elastic net, which is very similar to the combination of these two methods. It also uses the L1, which is the absolute value, and L2, which is it's L1 to the power of 2 in order to penalize the coefficient. And also you have other methods that we unfortunately due to time restriction cannot discuss, like decision trees, random forest, and things like that. They can help you select the most appropriate feature. With these methods, which is automatic, it's more accurate than the filter methods that we discussed in the beginning. It's faster than the wrapper methods, but it can be very complex to implement, and they're also very prone to overfitting if not handled correctly. This is guaranteed that it's going to be optimized. It's guaranteed that it's going to optimize the performance of the model for the data you have. Important. And then you have a balance between the performance and speed in regards to the filter and wrapper method that we discussed earlier. Okay, so this is in order to select we discussed how you can select the important feature for the analysis. But the question is that can you extract more information from the data you have? For example, it's called feature engineering. So for example, you can extract, it is a process of creating new features or even modifying the existing one in order to extract more knowledge and improve the performance of the machine learning. And then we are going to discuss two more methods, which is the domain knowledge-based feature engineering and the automated feature engineering. What do we mean by feature engineering? Is, for example, it uses specialized field-specific knowledge, usually from the expert, in order to enhance the database. It also can unveil key relations between a feature of your dataset, which is not directly observed. And also, you can use these new features in order to perform the performance of the model, and also can use the adjust existing feature based on the expert insight. I'm going to show you an example. For example, if you are dealing with the price, predict the price of a house. For example, in your data set, you may have the total price and the size in square meter. What you can do, you can combine these two features and create a price per meter byte. So, for example, you can use this to calculate a new feature called price per meter. You know how expensive the house is per meter, or how it costs per meter, which is also very important, adding new knowledge, but it didn't exist in your data. It was calculated from existing knowledge. So it's called feature engineering. So this requires the knowledge of the expert. Extract this knowledge. How do you know if you need extra feature that you are not aware? And so, for example, this can significantly improve the performance of the models. Also, they can improve the interoperability of the features. But the other negative thing can require significant domain knowledge and also can be very time consuming. Use it if you strongly understand what is in your data. And then the interoperability of the model is also very important. So it's very important for you to understand which feature is used and how you can use it as an expert. Use this prediction in the feature used to make a prediction. So interoperability is very important. If you cannot do this manually, you can use this automated feature engineering, which you may not have when you have high-dimensional data, or you don't actually necessarily understand the feature. You can use it automatically. What it done usually can have polynomial feature. Polynomial feature is exactly the same feature in the power 2 or power 3, You can have the interaction picture, which involves the product of random picture or multiply random picture and see if it can significantly improve the picture, or it can have aggregation data. You can group different data together using the mean or maximum value. This is done automatically. This because done automatically saves time and effort. So can discover complex patterns across multiple table of data, and also can, but this negative is can also generate large number of features, and the feature may not be interpretable. You may not entirely understand what the picture represents. And use this if you have a large data set of complex relationships, and then you don't necessarily understand what you are not the domain expert of this data. Okay, the cross-validation is different techniques that I'm going to keep for this presentation, but the most important thing is to be able to validate to have the metrics in order to validate the performance of your model. And usually, I will give you some examples. If you have a classification model, in the literature, you use this method accuracy, precision, recall F1 score, and AUR commonly used. And if you have regression model, you can use mean absolute error, mean square error, and root mean square error. So it's important to understand which is the final goal and to use the appropriate metrics for your to be able to evaluate your model. So if I'm going to show you an example online, I gave you this link. Also upload the code. I'm going to go through very quickly how you can implement these features we said very quickly, and then you can also try it on your own. And then if you have a question about how we implement it, you can contact me. I'm going to go through the code for 5 minutes, and then 10 minutes, and then you can handle it on your own. So if you follow the link, you're going to see this Python code. The data that we use is this, for example, there is this very old data set about the passengers of Titanic and how we can use this. What is existing in the database? You have the class of the passengers. What exists in the database? You have these classes. For example, what kind of type of class the passenger was traveling. It can be 1, 2, or 3. In your database, you have a Boolean value indicating that if the passenger actually survived Titanic. And then you have the name, the sex, the age, the number of siblings or spouses they traveling abroad, the parts, how many parents or children they have with them abroad, the ticket number, the fare, their cabin, if they actually from where they embarked. I mean, because Titanic embarked from 3 locations, actually where they get on. If they got on a lifeboat, their port identification number, if they have one, and where they are going. For example, different other parameters you have in your data sets. So the first thing, so this is what exists in the database. So for example, in this database, because imagine it is collected many years ago, it's an incomplete data. So you have many missing information, many incomplete, many wrong things, many wrong values in the. So you have these 14 attributes, and then you have for 13,000 records. So this is an Excel with many inconsistency, many missing values, and things. So how you can download? So now it exists for free in the online. You can use this code in order to be able to download for your own. the way the code runs, I provided the online code where you can run if you have Git Google Colab, or you can download it and run it on your own machine. So for example, the first case scenario is they are going to see what happens if you handle directly this kind of data set with missing values. The first thing that you want to do is because you have a lot of missing values. The first case scenario is just remove these features, remove them, or just don't use them. So, for example, the cases where you have missing values is the names, the age, the sex, the ticket number, the capital one, and which port they embark. So, this kind of thing, they are incomplete in your data. So, for example, the first case scenario is just to drop everything from your data set, and then we are going to split into training, and then we are going to use machine learning model. We are going to use a very simple logistic regression model. I'm not going to explain what exactly logistic regression is in this example, but if you want, can discuss later how this this model represents. But it assumes non-linear relationship between the inputs and the output, if they survive or not. Okay, so we train this logistic method for 1,000 iterations, and then the accuracy, this model uses the raw data from your model, and is able to predict with 71% accuracy if the passengers survive the journey or not, without actually having it. So it's fairly good accuracy with 71% with so the goal is that can you improve this accuracy better by filling the missing values, by handling the data a little bit better, but not improving the model, not using a more sophisticated model, just handling the data, cleaning the data in a more appropriate way, and see how the same model can be improved. So the thing is just to reload. So for example, the first thing that you identify is that you drop unnecessary columns, drop unnecessary name. The name of the passenger actually doesn't matter, or the number of the ticket, if it's survival or not. So if this is identified, in this case, because we are knowledge experts, we know that these features are not related to the dataset. Then we feel missing values. For example, the age, some cases not known. In this case, we are going to take the median value of all the passengers, and every time we have a missing value, we are going to replace it with the median value. You can choose something else. You can choose the mean, the mode, things like that. In this case, we choose the median. Then we convert the categorical variables to numerical. For example, which cabin they have, if they are sex, the male or female, converted to 0 and 1. We do one for encoding, for example, if it embark, which port they embark, we can have, and then you can scale it as it is, and then you can create a new feature, because you can see you have new feature family size, and then we have batch, how many children or siblings they have, or how many. So this one we can merge this and see how many family members they have with them. So we can merge it and create a new feature called family size. And then you can do standard scaling. In this case, feature like age scale. And then we apply it. We are going to give you the code, how you can do it. And then we retrain it using regression, and see the accuracy actually improved by 10%. So you can only have by handling these missing values and do some scaling, improvement went from 70% to 80%. And then you can do some cross-validation and see if you how you validate the model, how you split the passengers is important. So if you do this cross-validation, you can see you are expecting test accuracy to be around 85%, with plus or minus 6%. And then you can use this model with 80%, 85% accuracy, predict using this incomplete data, how accurate, if the passenger survived Titanic or not. Okay, so I will give you the codes. I hope you enjoyed the presentation. And then I think I will close the presentation now, and then you can ask any questions you have.